The cosmos is overwhelmingly vacant, and that vacancy may not be a mistake. It may be the central condition that makes everything else possible. Sit with that for a moment. For centuries, we have built telescopes, sent probes beyond Earth, and aimed radio receivers into the dark, all in search of something else. Life, a signal, another mind, and again, with a consistency that can feel almost rude, what we encounter is silence. Cold stone, frozen vapor. Worlds blasted by radiation, enormous stretches where nothing appears to be happening. But there is a detail that rarely makes the headlines. The scale of that silence is astonishing. This is not merely a universe where life seems uncommon. It is a universe containing perhaps trillions of galaxies, each holding billions or hundreds of billions of stars, while the only world known with certainty of host life is one small blue planet circling an ordinary star. Either life is far rarer than we intuitively expect, or we have not yet understood what all that apparent emptiness is doing. Because if you follow the question far enough, the barren worlds may stop looking like a failure of the universe. They may begin to look like one of its essential features. Imagine a Saturday morning. You are 8 years old, and someone gives you a bag of 200 marbles in every color you can think of. You spill them across the kitchen floor. They roll under the refrigerator, behind cabinets, along the tiles, and you spend 10 minutes crawling around to retrieve them. Now imagine that you find 199 without much trouble, but the last marble is gone. You check every corner. You press your cheek against the cold floor and look beneath every appliance. Nothing. Then, eventually, you spot it jammed into the narrowest impossible space between the dishwasher and the wall. One marble, hidden away, the single marble that seemed hardest to find. That is one way the universe feels to us, a vast scattering of worlds. And we seem to occupy the one place where chemistry woke up and began to notice itself. But here is the question people seldom ask when they picture that scene. Why were there 200 marbles in the first place? If one living world were enough, if life were somehow the objective, why create a kitchen floor so enormous that nearly every marble disappears into the distance? Why not 10? Why not 1? That apparent extravagance is where ordinary intuition breaks down. Carl Sagan's point was that the universe owes no obligation to human hopes or human convenience. Fair enough, but the cosmos can appear to be saying something even stranger. It has no obvious interest in efficiency. It spans roughly 93 billion light years across the observable portion alone, contains places no person will ever reach, and leaves you standing in a kitchen with coffee in your hand on a world that somehow became aware of all of it. That can feel beautiful. It can also feel terrifying. It may be both. Every generation of scientists has returned to some form of the same question. Are we alone? It is a powerful question. It is a question that helped create astrobiology, inspired radio searches, filled libraries of science fiction, and kept observatories listening for decades. Are we alone? Is there anyone else out there? But beneath that question is another one, quieter and less often placed on a magazine cover. Not whether we are alone, but why the question is even difficult. Why would a universe capable of producing life also be so remarkably effective at producing everything else? Why would the same laws that allowed amino acids to assemble in an ancient ocean also make gas giants with nowhere solid to stand, methane lakes on frozen moons, and rogue planets wandering through interstellar darkness? There are billions upon billions of objects that can never support anything remotely like us. Most of the time, we treat those places as scenery, background material, cosmic filler occupying space, while the important thing, life, happens somewhere else. But what if they are not filler? What if the lifeless worlds are the normal result, and life is the exception? Or perhaps, and this is where the idea becomes genuinely interesting, what if life and emptiness are not opposites at all? What if they are connected? What if the conditions that permit life also require a universe that is mostly empty? The deeper question is this. Could life exist in a universe packed tightly with matter, stars, and planets instead of one spread across immense dark distances? The answer is not known in any absolute sense. But modern cosmology strongly suggests that long-lived structure, stable stars, and complex chemistry depend on a delicate balance between matter, radiation, gravity, expansion, and time. And that balance changes the way the night sky looks. Open an introductory astronomy textbook, and you'll find a familiar explanation for why life might be scarce. Life requires a precise collection of conditions. It probably needs liquid water, which means temperatures in a limited range, which means orbiting at an appropriate distance from a suitable star. It needs an atmosphere stable enough to protect the surface, yet not so dense that it becomes hostile. It may need a magnetic field, chemical cycles, geological activity, long periods of climate stability, and billions of years for chemistry to become biology. Some researchers also argue that giant planets, impacts, plate tectonics, moons, stellar behavior, and galactic environment could matter. The odds of all those conditions meeting in one place may be small, very small. So the simple answer is that life is rare because habitable conditions are rare. This family of ideas is often associated with the rarer hypothesis, the possibility that complex, multicellular life requires an unusually specific combination of circumstances. It is a neat explanation. It fits comfortably into a lecture slide. It gives an answer without forcing anyone to stare too long into the void. But it does not settle the larger puzzle. It may explain why life is uncommon. It does not explain why the cosmos is so immense. If rare conditions are the entire story, if we are simply an unlikely outcome of cosmic lottery, why are there so many tickets? Why a universe with trillions of galaxies and perhaps more planets than any mind can meaningfully count? Why construct such a vast stage for such a seemingly improbable event? Saying that life is rare tells us something about life. It says far less about why the universe has the size, age, and structure we observe, and then physics adds another layer. In 1998, two teams studying distant supernovae expected to measure the universe's expansion slowing under gravity. That was the natural expectation. The Big Bang had sent matter outward, and gravity should have been steadily applying the brakes. Instead, the data pointed toward accelerated expansion. The universe was not simply expanding. Its expansion appeared to be speeding up. The discovery later earned the 2011 Nobel Prize in Physics. The name given to the unknown cause is dark energy, a label that describes our ignorance more than our understanding. Whatever it is, it behaves like a component of space that becomes increasingly important as the universe grows larger and matter thins out. Empty space, in that sense, is not entirely empty. It has measurable consequences. The cosmological constant associated with dark energy is also connected to one of the deepest puzzles in theoretical physics. Its observed value is extraordinarily small when expressed in Planck units, roughly around 1 part in 10 to the 120 or 122, depending on how the comparison is framed. If the vacuum energy had been much larger and positive in the early universe, expansion could have accelerated so quickly that matter would have struggled to collapse into galaxies. No galaxies would mean no stars, no heavy elements, no planets, and no familiar path to life. If the cosmic ingredients had instead produced a universe that recollapsed too quickly, there would have been too little time for stars and chemistry to develop. The point is not that physicists have proven the universe was built for life. They have not. The point is that the balance between expansion and gravity matters profoundly. The vacuum, the dark distances, and the ability of matter to gather into structure are part of the same cosmic story. Picture a thought experiment. Step outside yourself for a moment. You are not a person on a planet anymore. You are a physicist with impossible powers and a blank canvas. Your assignment is simple. Create a universe that can eventually produce life. You are free to choose the rules. At first, you might aim for efficiency. Why use more matter than necessary? Why allow endless empty space? Why not make a compact universe with one galaxy, a few 100 billion stars, and a reasonable number of planets around them? Then you run the model. The details immediately become complicated. Change the overall density, expansion history, or initial fluctuations, and you may change how quickly the universe cools. Alter those conditions too much, and the early mix of light elements changes. Make gravity dominate too strongly, and the universe may collapse before stable stars emerge. Make expansion dominate too early, and matter may never gather into galaxies at all. This does not mean scientists have demonstrated that only a universe of exactly our observed size could host life. They have not. A universe can be spatially much larger than the observable universe, and its total size remains unknown. But it does mean that life as we understand it requires a remarkable amount of cosmic preparation. It needs time for hydrogen and helium to form. It needs stars to ignite. It needs massive stars to forge carbon, oxygen, phosphorus, iron, and the other ingredients of planets and bodies. It needs supernovae to scatter those elements. It needs new stars and planetary systems to form from the debris. It needs planets to remain stable long enough for chemistry to become more than chemistry. Remove too much time, stability, or room for structure to develop, and the chain breaks. In that sense, life and cosmic emptiness may arrive together. They may be parts of the same package. Think of bread rising in an oven. For the loaf to expand, yeast produces tiny pockets of gas throughout the dough. The yeast is not carefully aiming at one special bubble. It works through the whole mixture. Most of the dough remains dough. Only a small fraction becomes open space. Yet without the surrounding bread, the bubbles could not form or hold their shape. Life may be like those bubbles. And the universe, the dark distances, the stellar furnaces, the dead worlds, the unoccupied light years, may be the dough, the medium in which something rare can appear and persist. The universe is not necessarily empty in spite of life. It may be spacious because the processes that eventually permit life require a universe with long-lived structure. Cosmology has long wrestled with a related issue called the flatness problem. Observations indicate that the universe is extremely close to geometrically flat on large scales. In cosmological terms, that means its overall density lies very near the critical value, separating a universe that would rapidly recollapse from one that would expand too quickly for matter to gather efficiently. Measurements place the density parameter, omega, extremely close to 1. In simple versions of Big Bang cosmology, without inflation, that closeness becomes more difficult to explain when projected back toward the earliest moments. A tiny departure from balance would have grown over time. Cosmic inflation was proposed partly to explain why the universe appears so flat, smooth, and large. Whether inflation is the final answer remains an active question, but the underlying lesson is clear. The early universe had to evolve in a way that left enough time for structure. A universe that collapsed almost immediately would never make stars. A universe that became too diffuse too fast would also struggle to make them. Stable expansion across billions of years is not a decorative detail. It is the reason there was time for stellar chemistry, planetary geology, and biology, and that realization can be difficult to look at directly. It suggests that life is not floating randomly inside a completely irrelevant cosmos. Life is an outcome made possible by a very particular history of physical conditions. That does not prove intention. It does not prove a designer. It does not prove that humans are the point. But it does mean that the conditions allowing observers cannot be neatly separated from the conditions that made the universe old, vast, structured, and mostly empty. The emptiness is not simply waste. It may be part of the scaffolding. Move now through the scales, from the smallest to the largest, and a similar pattern appears. A hydrogen atom, the most common type of atom in the universe, is mostly open space. Its tiny nucleus occupies a minuscule central region, while the electron exists as a quantum probability distribution extending far beyond it. If the nucleus were scaled to the size of a basketball, the characteristic size of the electron cloud would be hundreds of meters away. Atoms are overwhelmingly empty by volume, but that emptiness is not meaningless. It is created by quantum mechanics, electromagnetic forces, and the wave-like behavior of electrons. Those properties give atoms their size, their stability, and their ability to form molecules. Change them drastically and chemistry disappears. No stable molecules. No water. No proteins. No life. Your body contains roughly 7 times 10 to the 27 atoms. If all of its matter could be compressed to nuclear density, it would occupy only a tiny volume, on the order of microscopic grain rather than the size of a person. You are made largely of space held and formed by forces, fields, and quantum rules. You are an arrangement of almost empty atoms contemplating an almost empty universe. Our own solar system tells the same story. It contains 8 planets, dwarf planets, moons, asteroids, comets, dust, and countless smaller objects. Yet the sun accounts for more than 99.8% of the system's mass. The rest is scattered over distances so large that a spacecraft can travel for years to what appears to be nothing. The space between planets is enormous even before we leave our own neighborhood. Zoom out again. The observable universe spans roughly 93 billion light-years in diameter. Ordinary matter, the atoms making stars, planets, gas, dust, and people, account for only about 5% of its total energy budget. Dark matter contributes roughly another quarter, while dark energy makes up most of the rest. The average density of ordinary matter in the universe is only a fraction of a hydrogen atom per cubic meter, while even the total matter density is astonishingly thin by human standards. The best vacuums produced in laboratories on Earth can contain far more particles than the average reaches of intergalactic space. At atomic scales, planetary scales, solar system scales, and cosmic scales, absence is not merely the lack of objects. Space itself is part of the structure. Remove or radically alter that space, and the system no longer works as it did. There's a concept called the anthropic principle. It has been debated, misunderstood, stretched too far, and sometimes used as a substitute for explanation. But in its simplest, honest form, it says that any universe observed by living observers must be compatible with the existence of observers. At first, that sounds like a tautology. Of course, we find ourselves in a universe where we can exist. We could not observe one where we never formed. Fine, but the statement becomes more interesting when you consider the physical conditions that had to remain stable across cosmic time. The cosmological constant, the strength of gravity relative to electromagnetism, particle masses, nuclear forces, the properties of stars, and the chemistry of carbon are all subjects of serious fine-tuning discussions. Scientists disagree about how finely tuned some values truly are, how independent the parameters may be, and whether deeper laws could determine them. Still, small changes to certain physical constants can produce radically different universes. Stars may not form, atoms may not be stable in familiar ways, heavy elements may become scarce, or the universe may evolve too quickly for complex structures to arise. These parameters do not merely permit a planet like Earth in isolation. They shape the entire cosmic timeline required for heavy elements to be made in stellar cores, scattered by dying stars, gathered into new planetary systems, and transformed by geological and biological processes into beings capable of asking questions. From the Big Bang to a person looking at the sky, the process took roughly 13.8 billion years. It required duration. It required stability. It required stars, galaxies, and immense stretches of space. And here the apparent magic trick begins to reveal its mechanism. Empty planets are not necessarily evidence of cosmic failure. They are not automatically evidence of intent either, but they are evidence that the universe had enough material, enough time, and enough opportunities for rare things to occur. Every lifeless world may be a ticket that did not win. Yet a cosmos with countless tickets has more chances for any winning ticket to exist. We are not demonstrably alone in a universe of dead planets. We simply do not yet know. But we are the known result of a universe large and old enough for complexity to emerge at least once. Then the discomfort returns. Because physics, however beautiful, does not close every loop. Even if the universe needed to be old, expansive, and delicately balanced for life like ours to arise, the underlying question remains: why is there a universe at all? The apparent fine-tuning of physical conditions has several possible explanations. Perhaps there is a multiverse, an enormous ensemble of universes with different parameters, where observers naturally arise only in the rare regions compatible with complexity. In a sufficiently large ensemble, a life-permitting universe need not be miraculous. It would simply be one possibility eventually realized. But that explanation creates another question. What produces the multiverse? What establishes the rules that generate universes with different laws? Or perhaps the laws are not arbitrary. Maybe they are necessary consequences of a deeper mathematical structure we have not discovered. Maybe reality could not have been fundamentally different. Not because something chose its rules, but because consistency itself has limits. Or perhaps the word why is the problem. Maybe it is a human category imposed on a universe that existed for billions of years before humans appeared, and may continue long after humans are gone. Every empty planet is a question left unanswered. Every barren moon orbiting a distant giant planet is a reminder that the universe follows rules we are still learning to read. And perhaps the deepest question raised by all this emptiness is not whether we have neighbors, It is whether existence needs a reason at all. Imagine a planet no one has cataloged, no probe has visited, and no telescope has resolved clearly. It circles a dim star near the edge of a galaxy 400 million light-years from Earth. It is rocky, a little larger than Earth, with a thin atmosphere of nitrogen and carbon dioxide. It sits in the region astronomers call the habitable zone, and perhaps it is completely lifeless. No microbes, no spores, no chemistry that cross the threshold into biology. Just rock, wind, impact craters, and slow geological change. It may have existed for 4 billion years and continue for another 5 before its star evolves and consumes it. Across 9 billion years, nothing on its surface may ever move with intention. Nothing may eat. Nothing may wonder. Nothing may lift its eyes toward the sky. That is not necessarily a tragedy. It may simply be what most of the universe is like. But that imagined silent world would still belong to the same physical reality as you. The same laws that govern its atoms govern yours. The same expansion influencing the distance between galaxies also shapes the large-scale universe in which your neurons exist. Its emptiness and your awareness are not separate stories. They are consequences of the same cosmic conditions. The universe did not necessarily make billions of barren worlds instead of making you. It may be that a universe capable of making you also naturally makes billions of barren worlds. You are not proof that the universe is generous. You are proof that, at least once, its laws allowed matter to become alive enough to notice the silence. The universe is almost entirely empty. And that emptiness may not be an accident. It may be part of what made the question possible.